Let's start off with a quick review of chemical reaction equations. Hopefully at this point, an image like this should look rather familiar to you. Basically, what we're representing here is a reaction involving oxygen and hydrogen coming together or reacting to form water. Now we're representing this chemical reaction equation two different ways. We are drawing out the molecule O2, H2, explicitly, including the 1, 2 oxygen atoms and the 1, 2 hydrogen atoms, and we're using our standard shorthand notation where we are representing the molecular formula of oxygen and the molecular formula of hydrogen and water. So typically we represent a chemical reaction writing out just the molecular formulas like so. Alright, and of course everything on the left hand side of our reaction arrow here is termed the reactants, and everything on the right hand side is termed product. Okay. Now, oftentimes when we're dealing with chemical reaction equations, we are going to be a little bit more explicit, including more information, by including the state in which each one of the reactants and products are found. So in this case, we're going to be dealing with a reaction where each one of the reactants and the product is in the gas phase. Now, the types of questions we're going to want to answer here are as follows. Right? So suppose you have a given amount of reactant and we wanted to determine how much product can be formed. How much product can we form? Okay. And in order to do that, we're going to really have to examine the anatomy of the chemical reaction equation. So just to make sure that we're all on the same page here, let's start off by focusing first on this molecular formula and make sure that we are interpreting it properly. All right? So to do that, let's consider first the H2 molecules. All right? And let's consider this following question where we suppose that we have a dozen H2 molecules. And if we have a dozen H2 molecules, we want to determine how many individual hydrogen atoms we have. All right? So let's go ahead and break this problem down using our typical approach of first identifying what it is we're given. Okay, so now in this problem, we are given a dozen H2 molecules. We're going to represent this 1 dozen H2 molecules. All right? Now, we want to find how many individual hydrogen atoms. Okay, so we're going to determine the number of individual H atoms. So we're going to need a roadmap. We're going to start off with dozen H2 molecules. All right. And then we need to find some sort of conversion factor that allows us to go to number of individual H2 molecules. And then finally we will convert that to number of hydrogen atoms. Now, of course, this first conversion, converting from dozens of H2 molecules to number of individual H2 molecules, that's simply going to be our definition of the dozen, right? So we know that 1 dozen equals 12, right? 1 dozen H2 molecules equals 12 H2 molecules. And then to convert between the number of individual H2 molecules and the number of hydrogen atoms, we are going to have to use that molecular formula. Right? We are going to have to use the fact that for every 1 H2 molecule, there is 2 individual hydrogen atoms. So putting this all together, we're going to arrive at an expression where we're going to take our 1 dozen H2 molecules. We are first going to apply our conversion factor based on the definition of the dozen, right? Saying that 1 dozen H2 is 12 H2 molecules, right? So the dozen H2 are going to cancel out. Then we are going to use our conversion factor, which takes us from the number of H2 molecules to the number of hydrogen atoms, right? So H2 molecules cancels out here, and we are going to arrive at our final answer, which is simply 24 H atoms. So the take-home message here is that we are using this molecular formula as a conversion factor, okay? So the molecular formula gives us a conversion factor. Okay? And we're going to be essentially doing the same exact principle, but we are going to be applying this to the entire chemical reaction equation to be able to relate the different amounts of reactants and products, as we'll see shortly. But before doing that, let's do one more example where we can apply the same concept in a more realistic setting. So typical experiments, when you're carrying out reactions in the laboratory, you're not going to be dealing with individual atoms or molecules or even hundreds or thousands of atoms or molecules. Rather, you're going to be working with Avogadro's number of atoms or molecules. But as we're going to see here, the logic is exactly the same. So if we consider this problem where we're asked how many O2 molecules we can build from 5.42 moles of oxygen atoms. Right? So once again, we're going to start off with what we're given. Okay? In this case, we're given 5.42 moles of oxygen atoms. Right? And we're being asked to determine how many O2 molecules we can build. So our path is going to be similar, right? We're going to have, rather than individual molecules or dozens of molecules, we're going to be starting off with the moles of oxygen atoms. And we are going to convert from the moles of oxygen atoms to the number of oxygen atoms. And then finally, we will move to the number of O2 molecules. Okay, so we've got a two-step process just as in the previous problem. Although now our conversion factor to go from moles to the number of atoms is going to be given to us not from the definition of the dozen, but from the definition of Avogadro's number. So we are going to use Avogadro's number here, which states that there are 6.02 times 10 to the 23rd oxygen atoms for every 1 mole of oxygen atoms. And then once again, we will use our molecular formula as a conversion factor to build the conversion factor to take us from number of oxygen atoms to number of O2 molecules. So in this case, we are going to have every 1 O2 molecule, we are going to, of course, need 2 oxygen atoms. So writing this out, to build our final answer, we're going to start off with our 5.42 moles of oxygen atoms. We are going to multiply by Avogadro's number. And then effectively divide by 2. Okay. Carrying out this multiplication, we arrive at our final result of 1.63 times 10 to the 24th O2 molecules. Where again, the key part of this problem I want to draw your attention to is the construction of this conversion factor based on the molecular formula of the reactant molecule in this